In recent years, large language models have revolutionized software engineering, especially in the realm of code generation. Developers now routinely use models like GPT, Claude, and Gemini to draft entire functions, classes, and even full programs in seconds. But here's a critical question. Can these models actually write correct concurrent code? The answer, as it turns out, is far more complicated than we thought. Most existing benchmarks for evaluating LLMs focus almost exclusively on sequential code, simple functions that run from start to finish without interference. These benchmarks rely heavily on metrics like CodeBLEU, which measure how similar generated code is to a reference solution. But this approach fails when it comes to concurrency. Why? Because concurrent programs, where multiple threads run simultaneously, introduce entirely new classes of bugs that simply don't exist in sequential code. Race conditions, deadlocks, starvation, and uncaught exceptions under non-deterministic scheduling are all hallmarks of concurrent programming. And these issues are notoriously hard to catch with standard testing. Even worse, many LLM-generated programs compile, run, and pass basic tests, but still contain subtle concurrency flaws that only surface under specific thread interleavings. Static similarity metrics like CodeBLEU can't detect these. Unit tests can't cover all possible schedules. The result? A dangerous illusion of correctness. To address this blind spot, we introduce CONCUR, the first benchmark specifically designed to evaluate large language models on concurrent code generation. CONCUR is built around 115 carefully curated problems derived from Java Concurrency in practice, a standard textbook in the field. These problems form the semantic core of the benchmark. Tasks like implementing thread-safe counters, producer-consumer queues, readers-writers locks, and synchronized data structures. But we didn't stop there. To increase diversity and reduce memorization, we created 72 validated mutant variants of the original 43 problems. Each mutation preserves the core concurrency pattern, such as mutual exclusion or coordination via semaphores, but changes the wording, structure, or constraints. This ensures models aren't just regurgitating textbook solutions. Every problem comes with a structured prompt that explicitly defines the target language, Java 8, to ensure compatibility with analysis tools, the required number of threads and iterations to prevent state explosion, the need for a public main method, and strict rules against third-party libraries. Why? Because LLMs often generate code with too many threads, incorrect imports, or fragmented output. Our prompt engineering ensures that every response is a single, compilable Java file, no explanations, no interleaved text. But the real innovation lies in the evaluation framework. Instead of relying on unit tests or static similarity, we use model checking via Java PathFinder, JPF, a formal verification tool that systematically explores all possible thread interleavings within a bounded search space. This allows us to detect concurrency bugs that would otherwise go unnoticed. Our framework performs a two-stage validation. 1. Compilation check. We compile the generated code in a controlled JDK environment. Any syntax error, missing import, or third-party dependency is flagged immediately. 2. Model checking. For programs that compile, we run them through JPF with a suite of custom listeners that detect deadlocks, cyclic lock dependencies, race conditions, unsynchronized access to shared variables, starvation, threads never scheduled, uncaught exceptions, including concurrency-specific ones like rejected execution exception, missing entry points, no main method, single-threaded execution, a particularly insidious failure mode where the program uses thread-safe classes but never spawns multiple threads. This last category, single-thread SD, is critical. We observed that many LLMs generate solutions that look concurrent. They use concurrent hash map, atomic variables, or synchronized methods, but they execute everything in a single thread. The program compiles, runs without errors, and even passes unit tests. But it's not actually concurrent. Without explicitly detecting this, such programs would be misclassified as correct. CONCUR catches them, because concurrency isn't just about using the right tools. It's about executing in parallel. Now, what do the results show? We evaluated 23 state-of-the-art LLMs, including GPT-5, Claude Opus 4.1, Gemini 3 Pro, and open-source models like Llama 3 and CodeQwen, on the full 115-problem benchmark. The results are sobering. At pass at 1, meaning only one generation per prompt, even the top-performing models struggle. GPT-5 gets 77.4% correct, but many models fall below 10%. At pass at 3, where we allow 3 generations and take the first correct one, performance improves dramatically. GPT-5 jumps to 91.3%. And weaker models like CodeQwen nearly double their accuracy. This reveals a crucial insight. Multi-sample generation is essential for evaluating real-world LLM capabilities. Relying on pass at 1 alone severely underestimates model performance. But here's the kicker, CodeBLEU fails us. Despite high CodeBLEU scores, often between 0.45 and 0.58, many programs are still incorrect. Some models with moderate CodeBLEU scores, like Mixtral or Mistral, have pass rates below 3%. Others with high scores still produce deadlocks or race conditions. The median CodeBLEU for correct programs is only slightly higher than for incorrect ones, with massive overlap. This means high similarity to ground truth does not imply correctness. Static metrics are insufficient for concurrent code. We also conducted a manual audit of 115 programs that passed automated evaluation. Of those, 106 were confirmed correct, giving our framework a 92% precision. But the remaining 9 cases exposed deeper limitations. We found false positives where threads ran in parallel but didn't share state, effectively running independent tasks. Threads terminated prematurely without joining. Or values were incorrectly propagated across threads, even though no race condition occurred. These are not concurrency bugs, they're functional specification violations. And they're invisible to JPF unless you check the intent of the prompt. So what does this mean? It means that while LLMs can generate syntactically valid Java code, they often misunderstand the essence of concurrency. They know how to use synchronized, lock, and semaphore, but they don't always know when or why to use them. They design the logic conceptually, but fail to implement the actual parallel execution. This isn't just a flaw in current models. It's a fundamental gap in how we evaluate them. Existing benchmarks are built for sequential code. They measure surface-level similarity. They ignore non-determinism. They miss the very things that make concurrent programming so hard. CONCUR changes that. By combining a curated, diverse dataset with a formal verification framework based on model checking, we create a rigorous, reproducible benchmark that can detect the true correctness of concurrent programs, not just whether they compile, but whether they behave correctly under all possible thread schedules. We've made the entire dataset prompts and evaluation tools publicly available at Anonymous for Open Science R Concur 9DD4, and we maintain a public leaderboard at Concur Bench, GitHub, io/leaderboard, HTML, where new models are added regularly. This is more than just a benchmark. It's a call to action. As LLMs become central to software development, we must stop evaluating them on the easy problems. We need benchmarks that test the hard ones, the ones that matter in real-world systems. Concurrency is not a niche concern. It's foundational to modern software, from web servers to operating systems, from databases to AI pipelines. If we're going to trust LLMs to write production code, they need to be tested, not just on what they look like, but on what they do under real-world conditions. CONCUR is the first step toward that future. Because in the end, correctness isn't just about syntax. It's about behavior. And behavior under concurrency is not something you can guess. It's something you must verify. And now we finally have the tools to do it.